welcome to this lecture on polymers, where we are learning concepts and properties of these polymers, their applications and sustainability aspects. In this lecture, we will focus on biopolymers. We will do this by first looking at various ways in which we talk about classification of polymers, and then we will define biopolymers and then take a few examples of these biopolymers, especially with their applications in mind. So let's begin in terms of how we look at different types of polymers. So we could specify the type based on what is the nature of monomer or the repeating unit in the polymer. So for example, we could call something a hydrocarbon polymer, and of course immediately in your mind polyethylene will spring as an example, because it's just carbon and hydrogen. So many of the polymers indeed are hydrocarbons. Even polystyrene, for example, is where you have a benzyl radical, and so these are examples of hydrocarbon polymers. Carbon and hydrogen forming the backbone, and if there are branches and other molecular architectural details, they also will be containing carbons and hydrogen. As the name suggests, we could also have fluorinated polymers, and I don't know if you can think of an example which is used quite often in kitchens, which is a fluorinated polymer. I don't know if you can think of non-stick immediately. So non-stick pans have a Teflon coating, which all of you are familiar with, and Teflon is nothing but very similar in terms of molecular formula to polyethylene, but instead of hydrogen we have fluorine. So this is an example of fluorinated polymer. There are several applications of these fluorinated polymers in terms of their physical and chemical stability. So they are used as coating sometimes, like in case of kitchen. They are used as tubings whenever there is a possibility of corrosion, and then if we need a very stable material, then some of these fluorinated polymers are used as tubing materials. Polyelectrolyte is an example where we have an electrolyte attached to a polymer chain, and by electrolyte we mean something which can serve ionic conduction in its solution or melt or solid medium. And sodium chloride solution, for example, is the most common example of electrolyte that you can think of. In lead acid battery, we use sulfuric acid, which is again an electrolyte. So a polymer which can have ions, and this is one example. Again, you can see that many of these are very similar in that all of these are broadly made from monomers which are of this kind. So this monomer is very versatile. By changing R, we can achieve, if we change R, one example, we can get polystyrene. If we can change R to a carboxylic acid group, we get what's called polyacrylic acid. And this particular polymer, if I visualize it, what you will have is the polymer chain will have, let's say, a coil-like structure, and then periodically along the chain there are all these negative ions. And where do these negative ions come from? They come from this COH group. Basically, the COH group can dissociate, and therefore it can lead to. So basically, whenever we put this ion, this particular species, what we will have is water molecules which are surrounding, and then negative ions which are there on the polymer chain, and then there will be positive ions which are in the counter ions, which is nothing but proton. So this is an example of a polyelectrolyte. Conjugated polymer are very important from the point of view of conductivity. electrical conductivity. So many of the conducting polymers are conjugated. I don't know if you remember what is meant by conjugation. You can search for it. In fact, if it's alternate single and double bond conjugation, it's called conjugation. Maybe you remember that. You can search for it. And in fact, you will also come to know that in benzene, for example, there is conjugation, and that leads to delocalization of electron. And delocalization of electron implies conductivity may be possible. So that's why conjugated polymers are conducting polymers also. Sometimes when instead of every repeating unit having an ionic group, if there are few ionic groups on the chain, then it's called an ionic polymer. So for example, you may have an ionic polymer and few ions may be there. So what you have is many of the repeating units have no ionic group, but some repeating unit have ionic group. So for example, you could combine polyethylene and acrylic acid and make an ionic polymer. So you can have CH2CH2, which is what is polyethylene, and then if this is combined with CH2CH, COOH, and let's say what you do is you put lot more units of polyethylene, and so what you will have is a very small number of ionic groups on a polymer chain. So then it will look pretty much like this, where the polymer chain has few number of ionic groups. So these are called ionic polymers. And silicons are polymers where silicon and oxygen, as opposed to carbon, hydrogen or fluorine, some of the examples that we have seen. So we have also a very important rubbers and many other applications where silicons are used. And so this is one way of classifying polymers and thinking about different types of polymers. There's another way. Quite often we refer to a family of polymers, and this is based on whatever is the repeating unit or monomer in the polymer. For example, polyester clearly implies an ester bond, and we know that ester is formed based on a reaction between hydroxyl group and a carboxylic acid group. Similarly, we also have polyamide. Nylons are all examples of polyamide, and so here what you will see is a repeating unit like this. So this is called the amide linkage. What you will have is CONH. So this is how the amide linkage. So there are monomers which are attached with an amine functionality, and there are monomers which have an acidic functionality, and when these two react, we get what's called an amide linkage. Polyolefins, of course, are a very large class of materials. It's also very important because very large volumes of polyolefins are used. Polyethylene, polypropylene, two most important polyolefins, in fact, are bulk of the plastics that we use. Very high amounts of polyethylene and polypropylene is used. And so all of these are based on olefins. Another important class of polymers which are quite widely used are polyacrylates. So in this case, the acrylic group, if you remember on the previous slide, we looked at acrylic acid, polyacrylic acid. So which is nothing but CH2CH and COOH. So instead of hydrogen being here, if there are various other groups that can be substituted, then we get an acrylic family of polymers. So an important example of polyacrylate is polymethyl methacrylate, PMMA. It's quite commonly used, and in fact Perspex windows, which is a non-breakable plastic but optically very excellent properties, so that we can use them as glass materials. So they are used, PMMA. So as if you remember from last slide, so this is the acrylic group, but instead of that, if we have so this becomes methacrylic. And just to remind you, and instead of a hydrogen which was there on the polyacrylic group, if we have a methyl group. So, we remove this hydrogen and then we add. So, methyl methacrylate. So, acrylates are a very important class of materials. Polythiophene are materials which are very important class of conducting polymers, conjugated polymers. So, this is some examples of common families of polymers. We also can distinguish polymers based on what their origin is, and various polymers are called natural polymers because they are made by biological in the biological world from species such as bacteria to plants to animals, and so they are called natural polymers. And then we also have synthetic polymers which are quite often based on petroleum based raw materials. So, let us look at now examples of natural polymers which are called biopolymers. So, just to pause here and ask some questions and note some important features of these natural polymers. So, one thing which we have highlighted earlier also, that nature does use polymer or macromolecules, proteins, DNA, and there are several other examples whether it is cellulose, starch. So, nature does use polymers quite extensively, and these polymers or macromolecules in nature perform very important functions and variety of functions. So, it is they are very diverse and they can perform a mechanical role, they can perform a barrier role, what we need for, let us say, for a packaging material. They can also have a protective coating. So, various functions, they can provide conductivity, they can provide optical performance. So, basically whatever we need from an application point of view, all those roles are performed by macromolecules in natural conditions also. And so, based on the diversity of the requirements, we also have variety of macromolecules. In fact, cellulose itself can be made in various different forms depending on the species that requires it. Similarly, starch also. So, that is why, for example, in kitchen when sometimes when we use corn starch is different properties compared to some other starch, because each plant and each species has a specific requirement, and therefore, these biopolymers exist in variety of forms. And the key thing about these polymers in nature is that they do not accumulate as waste plastics. So, they within the natural cycles, the what are called the biogeochemical cycles, the generation and consumption of these chemicals, these macromolecules, is already built in. So, therefore, there is no accumulation of these waste plastics. So, this is a key indicator given the requirement of waste utilization and waste handling of plastics the way we use, and mainly these synthetic plastics. The question that we can ask is, given all these similarities with macromolecules of the natural polymer, can we not pose some questions to ourselves? Why can't we use polymers which nature itself uses? We need polymeric materials, we could borrow them from nature. Why can't we design polymers which are similar to natural polymers? So, that is another strategy. The natural polymer may not be able to exactly do the job that we are looking for. So, can we design polymer which has some of these advantages that we talked about in the way in the natural world macromolecules are taken care. Macromolecules are taken care in the sense that they are produced in a variety of different forms, they perform various different functions, and once their function is over, they become part of a cycle, so that they are consumed, they are degraded, and they therefore do not accumulate like plastic waste. And one more approach which we could take, can we modify the natural polymer so that they become suitable for the engineering applications that we want. So, therefore, this is a very useful set of pointers for us to think of new set of polymers that might help us take care of some of the issues related to sustainability of polymers. In this case, the raw materials that are required for polymers may also be part of the natural cycles, and since they are based on the physics and chemistry of natural systems, they are likely to become part of the biogeochemical cycles. So, just to pause and look at related terms to these biopolymers. Some polymers are called bio-based polymers, in which case the raw materials come from natural world. So, an important example of this is polylactic acid, and we will look at in little more detail renewable sources for polymers in lecture 8 also. So, polylactic acid which is considered to be a very good candidate material for packaging. It is a biodegradable polymer and it is made from corn sugar. We also have hydroxybutyrate, polyhydroxybutyrate, which is made by microorganisms, and this is also another example of a bio-based polymer, or polyols, which are based on sugar alcohol. And so, these are examples of polymers which are made from renewable resources or bio-based resources, and therefore, they are called bio-based polymers. Another important use of natural polymers, which is already used quite a bit, is in terms of natural fibers. We can extract fibers from variety of plant species, whether it is coconut we get coir fiber, from jute we can get fiber, from sisal. These are some other examples from banana, pineapple, so many plants are there from which we can extract fibers. And then these fibers, which are mechanically very strong, they can be used along with polymers as composite materials. So, you can make a composite of polymer and these natural fiber, and they are used. So, many quite often about a decade or 15 years ago, many automotive companies or many other transport based companies started saying that they are using green composite in their vehicles. What that implied was using a polymer, which was a synthetic polymer, along with a natural fiber, so that at least part of the material that they are using comes from natural polymers, and which can be again part of the overall cycles that are there in natural system. One other phrase which is used is biocompatible polymers. These are very different notation, though bio is common to all of this. Biocompatibility usually implies compatibility with human beings. So, the application here is in health or biomedical and within the human body. So, several class of synthetic polymers are also biocompatible. So, many materials which are used in medical implants need not be just natural polymers or bio-based polymers, they can be synthetic polymers also. There the requirement is that the tissue in our body has to be compatible with whatever are the foreign materials that we are implanting. An important set of polymers that we are looking for to avoid the overall complication associated with waste accumulation is biodegradable polymer. And so, here also again biodegradability does not imply that it is a natural polymer. Many synthetic polymers can also be made to be biodegradable. In fact, you will be surprised to know that there are some natural polymers which are not as easy to biodegrade. And so, that is so within the natural world also there are few polymers, select polymers, which time required for their degradation is much longer than many other polymers. And of course, this is part of the natural design, where some the functional requirements are always the key determinant of what a polymer property will look like. We will also look at the aspects of biodegradation in the lectures to come, and we will specifically look at the phenomena of biodegradation and the biodegradable polymers in lectures down the line. So, let us continue with our journey related to biopolymers, and these are also called, by the way, biomacromolecules. So, given that they are present in biological world and they are macromolecules. So, these are few examples again of how do we talk about different types of biomacromolecules or biopolymers. So, we could classify them based on the type of macromolecule. And this we have already seen in one of the introductory lecture, where proteins or DNA, RNA, which are examples of polynucleotides or polysaccharides. So, this is 3 different important sets of biomacromolecules which are present in the biological world. We could also classify them on the basis of which part of biological world do they come from. Do they come from a plant? Do they come from an animal? Or do they come from a microorganism? And so, here what I have done is given just a couple of examples of these biopolymers. So, casein is a protein which comes from milk, and pectin, which is there in variety of fruits and vegetables. This is from the rubber tree, polyisoprene or natural rubber, and xanthan gum is made by a bacteria. Of course, we have examples like gelatin, which comes from animal, and during the course later on we will have a chance to look at many of these polymers. One important thing that you can notice is, of course, these polymers are used. So, it is not that synthetic polymers are only used, a lot of natural fibers are used, as I pointed out earlier. Many of these biopolymers are also used quite commonly for variety of application. So, many of these biopolymers are used extensively, and for example, adhesive application, casein is used quite a lot. Pectin is used extensively as a gelling agent in foods. So, therefore, pectin also gets used quite a bit. Of course, natural rubber is also quite commonly used in variety of applications, whether it is tire or vibration mount and so on. Even in shoes or many other footwear applications, we use natural rubber at times. Also, in terms of modifying viscosity, thickener. So, that thickener is an application where we add a small amount of a material and that changes the viscosity. In this case, let us say if xanthan gum, the way it is used is we use it along with water, and then it increases the viscosity by orders of magnitude, and that is why it is called a thickener. So, you can see that very wide ranging applications of these biopolymers are present. And so, in this particular lecture, we will focus on 2 biopolymers, the xanthan gum and polyisoprene. And in a future lecture on conformations and structure of biopolymers, we will look at casein and pectin in much more detail. Just to remind you that these biopolymers are used quite extensively in various applications, and so it is important for us to recognize and understand concepts related to these biopolymers and how they are relevant in terms of being a model system for us to design new sets of materials from a sustainability point of view. So, let us look at the xanthan gum as an example. So, again it comes from a microorganism, but when you add this in water, it acts as a viscosity modifier or a thickener, and therefore, it is used quite commonly. It is made by a bacteria, as I mentioned already. It has a fairly high molecular weight, molar mass is quite high, and very important chemistry or physical chemistry of this compound is related to the presence of hydroxyl and carboxylic acid groups, which lead to very significant interactions, mainly hydrogen bonding in this polymer. So, whenever we put this polymer in water, because of interactions which are between xanthan gum and water, xanthan gum and xanthan gum molecules, we have a very rich behavior that arises. So, we have mainly a backbone, and there is also anions present on this. We will soon see that we have COO minus, and of course, a counter ion which may be proton in this xanthan gum case. And its applications are various, applications related to from toothpaste, foodstuffs like pudding and ice cream, and very important in crude oil recovery. We have a phrase called enhanced oil recovery. If you are interested, you can read more about it. In fact, many of the gums are used in enhanced oil recovery. Another important example of a gum which is very common, which is a biopolymer, is guar gum. Just try searching about guar gum and where does it originate from and who is the largest producer and supplier of guar gum, and you will be surprised that it is a vegetable which we are quite familiar with in different parts of India. Now, going further, the xanthan gum, depending on which state it is in, it can have a different molecular structure, and this is something which we will be learning in few of the courses down the line, few of the lectures down the line. So, generally as we have seen, we have been drawing a macromolecule like this. So, generally in a solution state, quite often it will be what is called a coil state, but for xanthan gum in solid state, what we have is an extended chain with a helical conformation because of hydrogen bonds. Because these hydroxyl and carboxylic acid groups are there, there is extensive hydrogen bonding possible in these materials, and in the end what you end up getting is some helical structure like this, and then it is an extended chain as opposed to a coil. So, therefore, this is called a extended chain. So, now going ahead and looking at the property which is important from the point of view of application, the solution state of xanthan, and interestingly here, depending on whatever the conditions of the solution, different states can be seen, different conformation states can be seen. So, the conformation change depending on what are the ionic interactions. How do we modify ionic interactions? Can you think of we have ions like CO minus, H plus, Na plus, K plus, Ca2 plus, SO4 2 minus, all these are ionic species, and they of course interact with each other. So, how is it possible to modify interactions between these? So, there are two ways to do it generally. One is by changing concentration of ions themselves, and concentration of ions can be changed by changing pH or by adding more salt or having less salt. So, what is called the ionic strength. So, one way to modify the interactions between ions is to change their concentrations or to change ionic strength of the medium. The other is of course temperature, because interaction with respect to the thermal energy which is present will determine how strong is the interaction, because thermal energy is always present, which causes the molecules to undergo different conformations. It allows bonds to occupy different energy states. So, thermal energy is always propelling molecules or bonds to change from one state to the other, and if interaction energy is strong, then thermal energy and interaction energy ratio is what is important in terms of determining whether the molecules and bonds will occupy one state or the other. So, flipping back and forth between different states is very crucially related to the interaction energy on one side and thermal energy. So, temperature will always play a key role in terms of determining how strong the interactions are. So, in case of low ionic strength or high temperature, you can see it's the ratio, right. So, whenever high temperature is there, the ratio is less. If the, so let us say ionic interaction is in numerator, thermal energy is in the denominator. So, you can see that how this both of these mean the same thing. So, if this is the case, when it is low ionic strength and high temperature, we have a random coil state, and if we have low temperature or high ionic strength, then we have a rigid helical rod. Now, one of the things that you may want to consider is whether this is just qualitative or can we actually get quantitative estimates of how much extended a chain is and how coil like a chain is, what is the size of the polymer chain when it is in coil state, or what is the size of the polymer when it is in extended chain. Yes, The answer is yes, we can get quantitative estimates, and in one of the future lectures we will talk about conformations, size, and what is meant by the length, persistence length of a macromolecule, which tells us whether it is a rod like molecule or extended molecule, or whether it is a coil like molecule or a flexible molecule. So, let us continue looking at this xanthan gum as a molecule. Just look at this diagram for the details. Okay. Look at the complexity of a biopolymer. What are the features that you can observe? Since the first lecture we have talked about variety of concepts. We have talked about backbone, we have talked about side group, we have talked about branching, we have talked about polyelectrolyte, we have talked about interactions between macromolecules, we have talked about degree of polymerization. Can you spot all of these things in this picture? And if you can, then you have got lot of grasp of these introductory aspects related to polymers. You can just pause here and maybe try to identify all the things that you can in this graph. Let us continue. These are all the features that are there in this, and this is the beauty of a natural polymer. Lot of variety of contents are there which allow lot of interactions to take place, and therefore, this polymer to exhibit one type of property or the other. So, of course, the backbone itself is there. You can see that there is a side branch. The molar mass of course depends on the degree of polymerization. The interactions. So, here very importantly we have intra-macromolecular and inter-macromolecule, and just the way we have been drawing a polymer macromolecule, you can notice that one part of polymer molecule can interact with another part. So, therefore, intramolecular interactions are possible, same macromolecule interacting with another. And of course, next to this we can have another macromolecule, and therefore, we also can have intermolecular interactions. So, in this case, all the interactions that are possible that we have talked about, for example, hydrogen bonding or ionic interactions, they are all possible between two xanthan gum molecules or within one xanthan gum macromolecule. The other important thing that we have spoken about is dissociation to lead to a polyanion, where polymer chain itself has a negative groups, and there is of course the counter ion. The counter ion is not drawn in this picture, but I am sure those of you who have been following the lecture will immediately spot that this is the COOH group, which leads to this polymer chain being polyelectrolytic or ionic. And so, what is of interest from a practical point of view is what are the conformations that a polymer molecule takes, and what is the state of interest in the. So, in this case it is the solution state which is of importance, and we would like to know whether it is taking an extended conformation or it is taking a coil like conformation. In terms of application, it might help for you to think of why should conformation depend on viscosity. Why should viscosity be determined based on what type of conformation a polymer takes? Just to think of this further, you could think of a beaker in which you have coil like objects, and how easy or difficult will be to stir this, as opposed to another beaker in which you have extended coil, not coil, extended chains of xanthan gum. So, if you want to stir one versus the other, clearly if viscosity is different, then the amount of energy required to stirring will be different. So, will it be different is something for you to think of, and we will look at this in a future lecture. Let us continue our journey and look at another example of a natural polymer. In this case, this is from a tree. Several trees are producers of gums and natural rubber, and most common that we use is a natural rubber tree, and this is an example of a cis polyisoprene. So, cis and trans isomers are possible. The application of natural rubber is elastomeric, something which stretches, and when you release it, it comes back. So, that is an elastic rubber band kind of an application. Quite importantly, in vibration mounts, natural rubber is still the most preferred material to be used, and in this case it is a damping application. An instrument or an equipment, when it is running, it vibrates, and that vibration will be passed on to the floor and from the floor to the other, and in fact the reverse way also. If something else is vibrating, it will come to the instrument and it might affect its functionality. So, generally this instrument or equipment is mounted on the floor, and there is a what is called a vibration isolation device which is used, because you do not want vibration from one equipment to carry to the other, or vibration of a floor being carried to the equipment, or equipment carrying its vibration to floor, so that the people around there will feel the vibration. So, vibration isolation is a very important application. It is there in vehicles also when we travel. So, this is a very important engineering application, and natural rubber mounts are extremely important in this vibration isolation application. What natural rubber is able to do is to absorb all the mechanical energy, and therefore, it does not transmit the vibrations. So, mechanical energy is nothing but vibrations, it absorbs all those vibrations and does not transmit the mechanical energy. Natural rubber is produced by trees using enzymes. So, proteins are used in catalysis. So, therefore, we call it enzymatic polymerization. Generally, we harvest this as a latex. So, this is a common term used in polymer science whenever we have a dispersion. So, if we have a dispersion of polymer or oligomer particles in a solvent. So, it is also called a latex. So, in fact, paints are also examples of latex. So, it contains some amount of rubber, and then of course, other biological chemicals, and then rubber has to be obtained by coagulation. So, in this case, coagulation is a process where dispersion is broken. Broken is a common English parlance term, but more coagulation is the term which specifies that these particles which were there will start coagulating with each other and then form exclude the solvent, and therefore, you can form the solid natural rubber piece. And so, just looking at how does a natural rubber tree's polyisoprene look like, here what I have shown is trans polyisoprene. So, I hope through your earlier chemistry knowledge, you should be able to draw how does a cis polyisoprene look like. So, just to draw this, if we have this H2C C, and then of course, if you remember from your this is the example of, so this CH3 group, and then this is H. So, this is an example of cis polyisoprene. So, as we have seen, rubber is obtained by coagulation of the latex, and in this stage natural rubber is not very useful, because it still will have more liquid like properties, and when we want to use it as a vibration mount, or when we want to use it as an elastomer, we need solid like character, where these latex particles should get joined with each other, and this is done basically by cross-linking the rubber. What is cross-linking is basically using sulfur to vulcanize, and this is something of course from school onwards you might have learnt about. So, if you have these rubber chains which are isolated, what you can do is incorporate sulfur and combine. And there are various interesting ways in which sulfur can interact, and so it can form a cyclic where it is not really cross-linking two molecules, it can form multiple S and then only it can form cross-link, and so variety of the chemistry of cross-linking of rubber is also very diverse. But generally we use sulfur vulcanization. There are other many cross-linking agents also using which cross-linking can be done. A biopolymer example that we looked at in terms of xanthan gum, we saw it was so rich in terms of the interactions. There were hydrogen bonding interactions, there were ionic interactions, and so everything was determined based on the strength and weaknesses of these interactions. In this biopolymer example, the interactions are in fact not relevant at all. In fact, this is an example of what we will call an ideal system. I do not know if you can remember which other context you have usually seen ideal in terms of a chemical in either thermodynamics or physical chemistry. We talk of ideal gas, and what do we mean by ideal gas? Is a set of molecules where there are no interactions. We say that ideal gas is molecules which can overlap with each other and so on. So, there are various ways in which we try to signify that interaction between molecules are not important when we have an ideal gas. So, similarly here when we have an ideal system, interaction between macromolecules is not very important in terms of determining its properties. So, this elastomeric properties as well as vibration mount properties, how can we explain them using no interactions? So, in fact, in this case the key is a segment of polymer. So, we have talked about, for example, a section of polymer chain between cross-link points, and this is a word which we have used earlier also, defined it, called a segment. So, what segments do is pretty much determining how will this rubber component behave. When we stretch the rubber for a rubber band, elastic rubber band kind of application, quite often we are doing this at a reasonably low rate, and so in this case the segments also get stretched, and when we release it, the segment want to come back to coil like state. So, therefore, interaction between segments is not important. How a segment gets stretched and how it comes back is sufficient for us to explain the elastomeric behavior of a rubber. When we are using it as a vibration mount, then again in that case we have a vibration mount. Let us say this is the mount, and then we have another component which is, let us say, vibrating, and this is basically vibrating either up and down or depending on the instrument. So, it is going basically this, while the bottom is the rubber component which is the mount. So, now what happens is, again the segments do not get stretched, but the segments start doing all kinds of conformational changes. So, a segment which was in one instant like this may change its conformation and become like this, again may change its conformation and become something like this. And so, what you have is segment keeps on changing its conformation. In this process, it absorbs the mechanical energy and dissipates it in the form of heat. So, therefore, whatever is the energy which is being transmitted by this vibrating part, it is absorbed in this vibration mount. So, energy gets absorbed, and in all of this explanation I did not really use how are the rubber macromolecules interacting with each other. So, therefore, this is an example where what segments are doing, whether they are getting stretched and recovering or they are changing conformations, and segmental motion basically can explain both elastomeric as well as vibration mount applications of this. So, here therefore, we have seen two beautiful examples of biopolymers. In one case, xanthan gum, where molecular interactions was everything that was important, and rubber, where molecular interactions could be neglected to explain the features of its application. Just to remind you again, when we say an ideal system, what we mean is molecular interactions can be neglected, and which is what we did in case of explaining elastomeric and vibration mount properties of rubber. So, with this we have come to close to this lecture on biopolymers, and we will continue our journey in terms of looking at now quantifying some of the features of the macromolecule. Thank you.